This is Physical Science 1, Chapter 4, Part 2 on the laws of motion. In this portion of the video lecture, we will continue our discussion on gravity and freefall. So when we discussed gravity and we talked about the acceleration of objects near Earth's surface and how the gravitational force of that 9.8 meters per second squared is the falling force of objects near Earth. So how would weightlessness or free fall occur? So when we think about gravity, remember gravitational forces, those are long-range forces, universal forces. So those gravitational forces never disappear. So really there are no zero gravity environments. There are microgravity environments, and that is how one becomes weightless in space. So as astronauts, for example, are either outside of the shuttle or the space station or inside, all of those objects seem to float because they're all falling with the same acceleration rate. So both the astronaut and the ship are falling towards the Earth, but they're falling at the same rate. So the objects, like the astronaut, would appear as though they're weightless. However, gravity is still acting on those objects. It's just that they're both falling at the same rate. So when we talk about motion and objects, projectile motion, we will be dealing with this a little bit with our catapult lab coming soon here. But Earth's gravity causes projectiles to follow a curved path. So gravity will make projectiles go into a nice arched path. So when we talk about horizontal and vertical motion, for example, a baseball pitcher, when you throw a ball, that force that's exerted as the ball pushes forward, that gives it horizontal motion. The horizontal velocity of the ball, if we ignore air resistance, should be constant. So if somehow a baseball pitcher could survive in a vacuum, if there was no air resistance pushing back on that ball, it would travel horizontal forever. But because there is air resistance, that ball will eventually slow down and fall to the ground. So when you let go of the ball, the moment that you do that, gravity, which is acting everywhere universally, is going to pull that ball downward. So you're going to have vertical motion as the ball travels in a curve. So there's an old physics experiment that says if you throw a ball in a perfectly horizontal direction, would it take longer to reach the ground than if you dropped a ball straight down from the same height? And the answer is they would drop at the same time. Most people think that if you throw a ball horizontally, it's going to take longer to reach the ground because it's traveling a longer distance. However, remember, both balls are traveling the same vertical distance in the same amount of time. But the horizontal ball will travel a longer distance. However, gravity acts on both at the same time. Both of those balls will have 9.8 meters per second squared of gravity pushing down on or pulling them down towards the center of the Earth. When we talk about motion in a circle, that is centripetal force. So when a ball or another object enters a curve, it will accelerate because the direction is not changing, or direction is changing rather, even if the speed does not change. So remember, it's like the merry-go-round. A merry-go-round can be at a constant speed, but it's always in a changing velocity because the direction is constantly changing. And so we call centripetal force that center-seeking force. So the force is being pulled into the center of that curve or that circle. So again, when a ball goes around the curve, the change in direction of velocity is always towards the center. So centripetal acceleration is acceleration towards the center of a curved or circular path. And centripetal force then is the net force that's exerted towards the center of a curved path. Now, when we talk a little bit about traction or friction in this case, NASCAR races, when the car rounds a curve on a highway, those centripetal forces act on the car to keep it moving in that curved path. And then the centripetal force is the frictional force or the traction between the tires and the road surface. This has been Physical Science 1, Chapter 4, Part 2 on Newton's laws.